that, we can start. So welcome all in this EuReComp webinar that will be presented by Aymen. Aymen, it's a technological center in Spain working on high-performance materials, on flexible production processes and systems, on robotics and automation, also on micro and high-precision manufacturing, on laser-based manufacturing, environmental issues, and additive manufacturing. Today, the two speakers that come from Aymen, it's Camilo Prieto, a senior researcher on laser-based manufacturing, and also Miguel Gomez Fernandez, who has professional experience on artificial vision and intelligence, developing and integrating different algorithms for automatic target detection, analyzing data from different types of cameras for smart identification for material classification. This will be the topic of today's webinar, so the inspection and identification technologies for the reuse and recycling of end-of-life composite materials. So Miguel will start. You may share your screen, and I would like to mention all of you that this webinar is recorded and it will be uploaded also in our YouTube channel. Thank you very much, and please, Miguel, the floor is yours.
Good afternoon, everyone. So I will start. So we will be presenting, thanks all for joining this webinar. We will be presenting technologies we are working at Aymen in the frame of EuReComp project to close the loop in the context of end-of-life composites and circular economy. So an outline for everyone to know what to expect. Here. Is an introduction on our institution, introduction to the project for those of you that don't know us yet. And then there will be two blocks of technology. First of all, inspection technologies. My colleague Miguel will present that. And then I'll continue again with identification technologies and conclusions. For each of the technologies, we will present the principle of operation, the instrumentation, the method, the systems required to perform these techniques, and some case studies in the context of the project for reference, and also an idea of how the software and the analysis is done to retrieve the required information for the applications at hand. So briefly, for those of you that don't know us yet, Aymen is a technology center located northwest Spain, very close to a city called Vigo, just indicated in that red dot in the corner in the map. Is northwest Atlantic coast. We have over 55 years of experience. It's a not-for-profit private association, headcount of 300 employees, and our core technology services and R&D activities are in the field of materials, advanced manufacturing, digitization, and sustainability. We are, I wanted to highlight also in these two main divisions, R&D and industrial divisions, on the green squares, the areas that are involved in the frame of EuReComp project. So circular lasers, you'll understand why, because we are using lasers for materials characterization. Smart manufacturing and inspection is what Miguel will be showing. So next slide, very briefly in a nutshell, because I refer, for those of you that haven't heard or read about EuReComp, I refer also to the website, and we have held a few webinars presenting different blocks of the technologies and the project itself. But in a nutshell, the concept of the project is quite well captured in this figure. It's a strong focus on circularity, and set out to provide sustainable methods, circular pathways for the end-of-life composites that are coming mainly for these industries, wind blades, aircrafts, and automotive. So after receiving those components, we can go, or we will go through different phases, or we are going through different phases in the project. Dismantling, separation, smart sorting is what we will be talking mostly today, to enable these circular pathways, repair, recycles. Once we have the recycled fibers under resins cover. We are also in the phase now of building and manufacturing demonstrators on the materials of the project. So in a nutshell, this is EuReComp, but today we will focus on inspection and identification technologies. So I'll hand over to my colleague Miguel because he will start with the first block. So Miguel, please.
Thank you, Camilo, for the introduction. A very important part of the project is the inspection analysis of the end-of-life composites like wind turbine blades or aircraft structures, as it allows us to identify the root causes of damage and to assess the integrity of parts for possible new uses, reducing wastes and promoting safety and sustainability. The most common defects that we can identify are delaminations, blisters, and cracks. The most efficient method for the inspection of defects is non-destructive testing, a group of methods used to evaluate the integrity, properties, and defects of composites without causing damage. There are multiple non-destructive testing methods, ranging from simple methods such as visual inspection to more complex methods such as radiography. In the EuReComp project, we mainly work with thermography and ultrasound testing. To put the following results into context, I will talk briefly about the study of piece in question. This is a 50 by 50 centimeter glass fiber reinforced polymer piece with artificially created defects. This plate is made with 12 plies of glass fiber with epoxy, making a total thickness of 10 millimeters. There are 25 numbered defects, both circular and square in shape, ranging from 5 millimeters to 25 millimeters in diameter, and found at 3 different depths from the surface: 2.5 millimeters, 5 millimeters, and 7.5 millimeters. In one hand, active thermography is dedicated to the acquisition and processing of thermal information. It involves the use of a heat source to stimulate an object with a heat pulse. Then, an infrared cooling process on the object. An infrared camera records a video of the object to measure the heating and cooling process of the object's surface. Its main features are high-speed scanning, which enable a fast analysis, and to provide two-dimensional thermal images, which allow a comparison between areas of the target. However, it has some issues such as non-uniform heating, lateral heat diffusion, and the environmental noise. To solve this problem as far as possible, post-processing methods are used. The most commonly used in this project are pulsed phase thermography, which is based in the calculation of the phase of a thermal image sequence using discrete Fourier transform, and principal component thermography, which is a statistical technique that reduces the dimensionality of a dataset and is used to identify specific patterns and analyze them to highlight differences in the image across the dataset. Most of the active thermography data have been taken using halogen lamps as a heat source, However, initial tests have also been carried out to prove the feasibility of using a laser as a heat source. Apart from the more obvious elements such as the laser as a heat source and the infrared camera to record the process, the laser active thermography setup has a diffractive optical element to give shape and homogeneity to the heated area, and a mirror or a series of them to be able to move the heat source away from the specimen in a reduced space. Although this particular setup has certain problems, such as the need for a smaller inspection area or taking into consideration the laser beam zero order, that is, the area where the laser is pointed directly, we have found the following advantages: homogeneous illumination, adjustable beam shape and size, modulable warming curve, selective analysis area, and a low scanning procedure. All these advantages allow us to detect some of the smaller diameter defects in the test plate. Moving to the second technique, we have the ultrasound testing, which is based on the propagation of ultrasonic waves in the object tested. Very short ultrasound pulse waves are transmitted into materials to characterize the material or for flow detecting. The depth of penetration for flow detection of this technique is superior to other non-destructive methods and is sensitive to surface and subsurface discontinuities. However, the surface must be accessible to transmit ultrasound, requires a coupling medium, and it's not easy to take the data and interpret it. So a technical expert is needed for that. The technique that we use in ultrasound testing is the ultrasound pulse echo. It uses a unique transducer which is connected to a flow detector and produces ultrasound pulse that is subjected to the test material during testing. If the transducer uses multiple receptor elements, as in our case, is called phase array ultrasound testing. The pulse travels through the material until it meets with a discontinuity or when it reaches a new medium. As a result, this wave is scattered or reflected back to the transducer. So, if there is no defect in the testing piece, the echo passes through the part and returns to receiver, showing only the input and output signals. Nevertheless, if the piece has a delamination or a porosity, a new signal appears, making even the output signal disappear in the first case, or a noise signal appears between the input and output signals in the second case. There are several ways of looking at the data obtained by phase array ultrasound testing. First, the A-scan is a radiofrequency waveform presentation showing the time and amplitude of an ultrasonic signal that represents the reflection from one sound beam position in the test piece. Then, the B-scan is an image showing a cross-sectional profile through one vertical slice of the test piece, showing the depth of the reflectors with respect to the linear position. The S-scan is an image that represents a cross-sectional view derived from a series of A scans that have been plotted with respect to time delay and, if is the case, refracted angle. The horizontal axis corresponds to test piece width and the vertical axis to depth. And finally, the C-scan is a two-dimensional presentation of data displayed as top view of a test piece, where color represents the signal amplitude at each point in the test piece mapped to its position between the depth selected. To finish talking about the inspection analysis, I would like to show a short video where you can see the software developed in the context of the project to work with
Miguel, I think you are mute.
Now?
Yeah.
Yeah. When I was muted?
Few seconds ago. So.
Okay, perfect.
Yeah.
So I repeat this slide. To finish talking about the inspection analysis, I would like to show a short video where you can see the software developed in the context of the project to work with NDT, called Thermography and Ultrasound Testing tool, and that you can find in Zenodo. In the video, you can see the analysis made on one of end-of-life aircraft parts provided by a project partner. We can first observe the analysis made with active thermography, that it's possible to distinguish areas where the solid carbon fiber is located from the areas filled with foam. In addition, it is also possible to distinguish where the screws are located, both using pulse phase thermography and principal components analysis. This analysis is made for both sides of the piece. Then again the same thing can be observed, but this time we using ultrasound testing. This concludes the inspection analysis part, and we give away again to Camilo with the chemical identification part.
Okay, you should be seeing now the second my slides with when we start the second block on identification technologies. To give you a bit of more context, as I was referring at the beginning, chemical recycling is a very active topic also for the project. Core technologies are developed here around solvolysis. And in this context, in situ material characterization, identification is one of the challenges. So we set as an objective, and as I meant, responsible of that, to develop innovative identification systems by means of spectroscopic techniques and advanced data processing. And those are the techniques I will present: hyperspectral, LIBS, Raman, and data processing by chemometrics and machine learning algorithms. To start with, as my colleague did, I'll providing for the purpose of this webinar a small set of the range and samples and materials we studied in the project and beyond, because here you can listed 6 types of materials or matrix systems, 4 epoxy resins and different type of hardeners. We also include in this batch vinyl ester and polyester, even though those are not specifically from wind or from automotive or aircraft, but quite extensively used. So no commercial names, but those are the material systems. And if we were looking at the chemical structure of these thermosets, we know our partners on chemical processing know very well the complex structures that these material systems have. But still, so that defines the scope of our work on these techniques, to identify, to be able to recognize them, not to analyze fully what it is the chemical formula, let's say. So then I'll move on to the second slide. I'll put on the pointer. And I'll start with hyperspectral imaging. In simple terms, spectroscopy is the study of light, of the interaction light and matter. Color imaging is what we are, or what I am showing here is the electromagnetic spectrum. And as humans, we are very used to the 3 colors on our phones, on our cameras. But what I'm presenting today is technology of vision that provides more spectral information, and we can distinguish among multispectral and hyperspectral. That depends on the number of bands. But basically, this technology combines the power of digital imaging and spectroscopy, because if we look in the 3 dimensions, we have spatial information on X and Y, but in Z we have the spectral information, and you can read either by pixel in this kind of reflectance spectra, or in volume. This is called hypercube. So the spectral data can be used to chemically identify the materials, and the spatial data provides spatial information where each material is. So it's a very interesting technology to explore for material identification as well, as combines best of both worlds, let's say. There are several technologies or ways to get an hyperspectral imaging. Those are depicted in this scan. Point scan, not much use at the moment. Line scan, where we have a prism to disperse the light onto a 2D detector. With filters, you can get the spectral scan, slow but also very effective in this. And recently, in the last years, I got quite a lot manufacturers provided the snapshot cameras, mostly for multispectral imaging sensors. That means less spectral bands, but also very effective, as in one picture you can get the hypercube, no? And these images shows how this hypercube is reconstructed for each of the sensors. But at timing, we have been working in the context of this project with line scan technology, another diagram. So the part is moving and is imaged through a slit and dispersed by a prism into a 2D detector. We have been investigating or using 2 technologies, or 2 detector technologies, silicon and InGaAs. So the silicon is sensitive in the visible range, a bit standard of our visible range, up to 900, and then the InGaAs in the so-called short wave infrared, so from 900 nanometers to 1700s. Those 2 sensors, you see, they have the same kind of appearance. Halogen lamps to illuminate the samples, and here in these areas are the specification of each sensor. No? So we have 3 spectral channels and 900 special channels in the case of visible, and 162 channels in the case of infrared. So a lot of information, spectral information. 2 different ways of illuminating, by reflection or by transmission. So that is also might be handy for some materials and for some specifics. For this project, I'm thinking how to implement or deploy this in next steps. We were investigating mostly reflection, as is the most practical in handling end-of-life components. And so I'll show you briefly some spectra from this set of samples I was referring at the beginning. So we are looking here, I'll guide you through the interpretation of this spectra. We are looking at reflectance spectra on the visible range, so wavelength, intensity of light coming back. This is pretty similar of what our eye can see, as I was mentioning, not totally on the range, but also our detector, our cones in the eye are located, or at least the phone images. But we can see, looking at the spectra, the different colors, that there are like two type of materials. You can see it also by the 3D color reconstruction, the images. That these spectral bands, so the reflectance intersects or overlaps or change, so that provides information about where are the areas where the materials can be better distinguished in terms of lighting and detection, but also what will be the spectral bands that an algorithm could use to automatically detect and develop, decide how to discriminate, differentiate among them. If with the same set of reference samples we are using for illustrative purposes today, we move on to the SWIR, to the shortwave infrared. So we are looking at the spectrum now beyond our eye, our vision, our human eye capabilities, from 900 nanometers to 1700. So those are for reference where these red, green, and blue channels are written. But looking at the spectra again, we can see areas, spectral bands, where the materials could be discriminated better than others. And this is basically the principle of hyperspectral identification of selection. Those bands will be part. We have here 168, if I remember well, bands. So those bands, those features of the spectra could be used to develop a discrimination model. Also interesting here, those of resins out of these 6 show an absorption peak here. So that gives you some indication on the chemical composition as well. And this is basically learned from the hyperspectral imaging. I'll move on to the second technique, and the second technique is LIPS. It's a different technique because it's an optical emission spectroscopic technique. So before it was absorption spectroscopy, now it's emission spectroscopy, and it's based on a high power laser pulse. It's focused on a given material. An ablation is taking place. Ablation means explosive vaporization of material. So high temperature, a small plasma is created. When this plasma cools down, light emission produced, and this light emission is corresponding to the elements that are present on this plasma. And at the end, a small crater, depends on the optics, but micro crater is on the material. So no sample preparation is required, multiple elements. So this is an illustrative also spectra that you can obtain by LIPS. So in one axis, wavelength again, and intensity on the other. All the elements emit or have specific wavelength emissions that are luckily tabulated and publicly available. So like any other atomic emission spectroscopic technique, you can use them. So that can be performed qualitative and quantitative analysis. In this case, on the project, we are interested in qualitative to determine what it is, not how much or what the amounts, but quantitative analysis can be done. And as it is not requiring sample preparation, it's also possible to perform in situ. It's a surface technique, but since we are ablating, we can also perform depth profiling, so a bit of penetration is possible. Material versatility in terms of liquids, powders, solids is possible, and gases, aerosols. What instruments we need to perform LIPS? So in a very schematic diagram, we can see it here, a laser to perform the ablation, optics to deliver the energy, to collect the optical emission, and to disperse this light onto a detector. So here I point to several elements we have in our R&D lab for LIPS that are lasers, different wavelength, pulse duration, pulse energy, and rep rate are available, usually for these studies, the rep rate is about 100 Hz in that range. So that gives you an idea how fast the measurement can be. Detections, also different detections systems for time resolved spectroscopy or for more field or industrial environments. Here I'll have another picture later how the laser is focused and the light is collected, and those also are variables of the system set, and of course computed a movement between laser and stage. In this case, we are moving the samples or the materials underneath to perform the spectral measurement on the material at hand. Zooming in the chamber of analysis, so we can depict here like how the laser is firing onto the sample. I think I have a small video here, hopefully as well. Sure. You can see here with a basic webcam that a plasma is created. So this is still not, and each of these pulses or sequence of pulses leaves micron-sized crater, as I was showing you before. That is this optical microscope picture. So come back to our intended goal, to discriminate materials. If we look at the high-speed imaging of two different materials, organic materials, two different resins, we can see that hopefully this video also goes, because those are snapshots of high-speed camera. Let's see if they play. Now they should play. So you can see one kind of orange light and other more like colorful rainbow, but this is basically the color, the spectral emission that is produced each of these different craters, and that's reported in a spectrum or one axis wavelength and another intensity. And the problematic here is that most of the resins and the materials that we are handling are basically formed for organic elements, so the spectra will look very similar. And so this, I was talking about the crater size. Let me tell you that the time of these events are microseconds, tens of microseconds of duration, and during that time, different light emission or different emission wavelengths are produced. We can capture them with our detectors, and we get the spectra similar to this, where when we go to those databases, we can identify what are the atomics. So we could predict most of the emissions corresponds to these lines, carbon, hydrogen, oxygen, but also nitrogen, that if it's not on the material, can be in the surrounding atmosphere. Some molecular emissions are possible. Now the new detectors enable to capture also those. So we get a lot of peaks and signals that we can record for each of these LIPS measurements. And this is how our starting point for the development of classification algorithms and models that are based on this spectral data and using the machine learning of learning from those data and from data sets and from data collection, extract models that can separate classes. Coming back to our use case today of the 6 material systems, we can show here what will be the outcome or one of the latest stages, not the final stage, but how these 6 materials can be identified. We can see this via these diagrams. One is a 2D representation of how each of these measurements are separated. This is by color, so you can see some classes that are quite different the beginning. So the 6, I think it was vinyl ester, is clearly distinguishable by 2 components. But the model can work with more than 2 components, and this is what is represented here in this matrix confusion. For those of you that are not familiar with the representation, so in one axis is the predicted label, and the other is the true label. So those values out of the diagonal are the measurements that the algorithm fails. So in this case, we get an overall accuracy close to 92% on this system. So that's quite good. and to show you a bit more on the inside of this, how this and all the steps that are in between, not only experimental, also from the data analysis part, both in the pre-processing, on the different normalization strategies, on what emission peak signals one can use, and how these descriptors, these features are selected to fit the algorithm and to train the algorithm based on these features. So it's a very iterative development process where we manage to improve and to optimize during the project and reaching those high accuracy that we are getting at the moment. So this is the basics path for development on LIPS that we are implementing here. In the case of thermosets, that is quite challenging because of what I said is mostly the emission lines are corresponding to organic, and all the materials present have those same elements in very similar stoichiometric or elemental ratios, but in different bonds and in different chemical structures that obviously have a replication. Information is in the plume when we ablate it, and this is what we take our algorithms and our models take as an input to deliver this output. And with that, I close the second technique, that is LIPS. We are moving on also to Raman. It's a third technique I want to present today. Again, another family, because it's a vibrational molecular technique in relines. I'll get back to the pointer. Relies on inelastic scattering of photons. I'll explain what is that. So when photons from a laser, can be lasers are available between UV, near, and beyond, but what normally is used in Raman are on those wavelengths, most frequently continuum lasers, but pulse can be also used. But when photons from a laser interact with molecular vibrations that are indicated here of a certain material, they can be excited to a high energy level. Most of this energy will be dissipated later through elastic scattering, also called Rayleigh scattering, where the energy of the emitted photons is equal to the photon from the laser. But the Raman spectroscopy and the phenomenon itself measures the wavelength of those photons that are inelastically scattered, and the emitted photons in those cases is higher or lower in energy as compared to the photon used for the laser. So this spectra of this inelastically scattered laser is what can be visualized in a spectrum of intensity over wavelength, as in the past. And this is what provides information on the bonds and on the material. So features of the method, we can get detailed molecular structure information because those emission or those peaks are material specific. In this case, it's not destructive. Normally, you use energies that don't ablate or don't damage the material. Could be, but most of the cases it's non-destructive. The signal is comparatively weak because, as I said, most of the transitions are elastic scattering, not inelastic. So that implies that we need some time to take the measurements. Good thing it is not affected by water interference, unlike infrared spectroscopy, the other vibrational spectroscopy that is very much used in the field of polymers, thermoplastic thermosets, among other areas. But in that, from this and from other perspectives, the two techniques, Raman and infrared, are very much complementary in terms of active functional groups that are active in Raman and infrared. And all with this information, we can perform what our objective, that is identification of materials. And actually is one of the, not only because have quite many use, but the most common use of the application technique in volume is material identification based on this fingerprint because of the selectivity of the method. As I did before, I'll present what instruments we will need and what is consisting about. I'll start with this simple diagram. I think it's easier for all to follow. So laser to study the material. We normally focus with a small onto a small spot to get enough photon density. And so in this case, the laser is green, but part of the light is mostly green, but there are inelastically scattering light. Those are the Raman emission that we are interested in. So we filter out the green with the notch filter, and we detect the other emission. So this should be shifted to the red normally onto the spectrometer. So basic parameters or basic configuration of the system are laser with the wavelength. I was mentioning before, different wavelength and different powers you can use, the probe geometry and the type, fiber configuration fiber probes are available, handheld probes are available. Also high sophisticated or lab systems like the one our partner in the project, Patronus University, is using, or more small systems that are converted optical microscopes are used, like the one we are using at IMEM, but optical collection is an important variable. And then the detection, not only for the spectral range, the resolution is very important that the detector have very low dark noise. Because of that, to collect enough Raman signal, normally you need longer times of acquisition, so the quality of the detector is important. I'll mention now that normally Raman takes place together with fluorescence or photoluminescence. With the same equipment, you get normally both effects. Photoluminescence is usually much stronger, so it's part of the process of handling the Raman spectra to remove that, among other data preprocessing methods. And as the other vibrational spectroscopic technique, how this is plotted normally is in terms of wave numbers. So the Raman shift calculation. So from the original spectra, Raman spectra, we convert it into wave numbers on the x-axis, and those are the Raman spectra we are about to see. So I'll explain the converted optical microscope where a laser diode is fit, a beam splitter focus onto the sample that laser, reflected back into an optical fiber that guides the Raman signal to the spectrometer. So after removing the fluorescence and all the pre-processing steps required, we can plot different Raman spectra, so we can see wave numbers and intensity. For the purpose of this slide, we selected those three that are resins or material systems I presented at the beginning, case 9, 2, 3, and 5. I think this is one is Vinny Lester. But even by naked eye, we can see clearly different Raman spectra, different fingerprints on these three materials. No? If we do, and we did together in collaboration with our partner again, Patras University, identification on the pinks, on the different peaks and the different structures, mostly the bisphenol on the epoxy units. Obviously, this one that is vinyl ester or polyester doesn't have the bisphenol. So we can identify the material-specific lines that allow us for the identification of and the differentiation from the other materials. So that is the basis or the information where the classification could be performed when applying Raman on this context. So I think with this, I'll conclude this second block, the presentation of the technologies, the concepts, the fundamentals of the technique, the instrumentation and the system required, and a bit also on the spectra interpretation, analysis, acquisition. Because I mean in Raman is not at all obvious and discrimination bad, but here even without full peak assignment and discrimination algorithm can be easily developed. And I would like to conclude with some takeaway messages. So today we have presented technologies for enable decisions or support decision on these material circularity pathways that we are tackling in EuReComp project. 2 blocks my colleague Miguel presented to first with a thermography and ultrasound testing, focus very much in the inspection and of parts and detection of defects, and support the decision on repair, reuse, and recycle pathways. Myself, I was just presenting those a bit on these 3 techniques we are working at IMEN: hyperspectral, LIPS, and Raman. I was trying to give you a overview of how the systems and the experimental protocols can be developed, and the power of coupling that with machine learning algorithms to enable differentiation of these systems. So with that, I would like to conclude, thanking you all for your attention. Both contact details of my colleague and myself are available here. And we are open for questions, if any. Thank you very much.
Thank you both, Miguel and Camilo, for a very nice and detailed presentation with all these characterization techniques that have been developed also within EuReComp project. I would like to start with a question related to the time needed in order to perform in real life these techniques when we want, for example, to inspect a wind turbine blade prior its dismantling. Can you please have an estimation on how these techniques can be performed in real life?
I guess this is for you, Miguel.
Yeah. For an entire blade wing, it depends if the camera can record all the turbine, or if only cuts a part. But for every part, more or less are 2 minutes for the recording video in the active thermography, 5 minutes or even less for the post-processing methods. And then see the results immediately in the system, but it takes a time to see all the turbine. Estimation of time starting ultrasound testing. So sorry if I couldn't answer your question.
We lost just from your reply. We just lost the last part. There was an interruption. If you can repeat just the last part.
Yeah. Transducer, but more or less instantly, but you can for all the turbine you have to take the time to take all the data on ultrasound testing, and not for me. So sorry if I can't answer the question very well.
Okay, there were some interruptions in the sound, but I think that we may proceed. Other questions from the audience before going to the next? Someone that would like to ask something, you can also add your question in the chat or raise your hand. Yes, Lefteris, please. You have the floor.
Hello, Camilo. Hello, Miguel.
Hello.
Thank you for the nice presentation. I have one question about the leads. Actually, there are two questions. The first one is if you can change the power of the laser and see differences in the spectra. The first question is this. And the second one is when you try leads in the composite, is it dominated by carbon, your spectra? Or you still can see other elements?
Yeah, even other elements. So to the first question, yes, sure, is one of the parameters of the system, the laser power, because with more power, more intensity, more material ablated, more signal, and actually the geometry even of the plasma effect. So this is one of the key parameters we record and we optimize, and the link with all other. And then, yeah, the power of the laser enables you to ablate more material and collect more signal, or in some cases to select what material you ablate, even in the case of heterogeneous material. And to your second question, that's for sure, yeah, one of the biggest challenges of the project, and how the impact of the fibers and the other elements that might be present in the sizing. So carbon increase. To your question, yeah, carbon certainly increase when we have carbon fiber. We detect stronger emission lines for carbon. But to reformulate or transfer the models that we have for the resins to the carbon-based composites is one of the challenges, as is what we are investing the time at the moment, yeah. And even I was saying, yeah, in some cases we have seen other elements, inorganic elements, that we are confident that they come from the sizing or from other additives that are present in the end-of-life components. That could be also a way or information that we could use to discriminate with a proper database of materials for our system, yeah.
Okay, thank you.
You're welcome. Yeah.
Other questions? Something that you'd like to ask? Okay, since also we're short of time, I think that we can close our webinar today. Thank you very much, both of you, Camilo and Miguel. And
Thank you.
With this closure, I would like to mention that we have within March the workshop that will take place in NTUA, in the School of Chemical Engineering. This will be held in our premises on the 29th of March. So you are all welcome to join us physically or through our online connection. There will be also a demonstration part. And in April, after the Easter Orthodox holidays, we will have the next webinar of our EuReComp Webinar series. So you are all welcome to join and follow us. Thank you very much all for your time and attention. I hope to see you soon again. Goodbye.
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 Bye bye.
Bye bye.
Bye. Bye.
Bye-bye. Bye.